Okay, can you hear me?
Yep.
Okay, thank you. So hello everyone, so thank you for coming tonight. I am Mayuko from Space Cafe Tokyo team. So let's get started. Oh, wait. Can you hear me? Oh. Sorry. So we are Space Cafe Tokyo team. Usually we have our monthly event at Good Heavens British Bar in Shimokitazawa, Tokyo. But according to this COVID-19 situation, we started our online event from May, I guess so. And hopefully we will back to the offline event in maybe 3 or 4 months. But for now, we're very happy to have online event and welcoming people from all over the world. So before we started, I have a few announcements. First, we will mute all the participants during the talk, and you can send comments and questions anytime in the Zoom or YouTube chat, and we will pick up the questions and read out them as many as possible during the Q&A session. And today, for the first trial, after the talk, we will have free discussion time. So then you can unmute and talk to each other after the talk. So if you join from YouTube Live, I think there are several people joining from YouTube Live. But then if you want to talk each other, then please register as a Zoom meeting and come here. Then you can talk with us. Okay. So today, the topic is atmospheres of planets around other stars. We invite Dr. Yui Kawashima-san from RIKEN. So after she got her Ph.D. in University of Tokyo, she worked as a postdoc at ELSI, Tokyo Institute of Technology, and at SRON in the Netherlands. And from past month, she started working at RIKEN in Tokyo. So Kawashima-san, hello.
Hello, nice to meet you. Thank you so much for inviting me today to talk about exoplanet atmospheres, which I have been working on for almost 8 years. Thank you so much.
Yes, so I will stop my share screen. So please go ahead. Thank you so much.
Mm-hmm. Can you see my slides now?
Yes, perfect.
Okay. Sorry. Sorry. Today I will be talking about atmospheres of planets around other stars. So before going to the main topic of this talk, I just thought it might be better to give a brief introduction of myself first. So I decided to prepare these slides. So I grew up in Kawasaki in Kanagawa in Japan, and my hobby is to travel and taking a work. And as Mayuko described, I did my PhD in the University of Tokyo, and after that I worked at ELSI, Tokyo Institute of Technology, and after that I went to SRON in the Netherlands and did 2 years of postdoc there. And from this month, I started working at RIKEN in Wakoshi in Japan. So let me first give an introduction. So this is the view of the Earth taken from the Apollo 11 spacecraft. And I think some of us might have the question like, are we alone in the universe, or is there any planets like our Earth? So let's first again see our solar system planets. So we know that we have multiple planets in our solar system. And our Earth is located from the certain distance from the sun. And this sorry, somehow I cannot read my throat. Sorry, somehow my keyboard does not work.
Oh, no worries.
Sorry. I'm so sorry.
It's okay, it's okay. So now it's like you cannot.
So somehow the keynote is freezed,
I
and
see.
I cannot even close the keynote. So
Maybe stop sharing and then close and reshare.
Yes, I tried. But I cannot even find the pointers somehow.
Oh, I see. So I try to stop sharing from my
Thank you.
side. Yes. How is it?
I think it's working now.
Ah.
Thank you.
That's good.
Let me share my slides again. Can you see my slides now?
Yes.
Thank you very much. I'm sorry.
It's okay.
So our Earth is located for certain distance from the sun, and this distance is called atomic 1 AU, and which is the distance between the sun and Earth. And we know that there are also other planets in our solar system. If we look the distant way from the sun, there is a Mars, and we also have the Venus and Mercury close to the sun. And if we if we look to the more distant part of our solar system, we have Jupiter and Saturn and Uranus and Neptune. And these 4 planets, such as Mercury, Venus, Earth, and Mars, are called rocky planets because they are their planet part is almost dominated by rocks. But on the other hand, Jupiter and Saturn are called gaseous planets because their body is almost dominated by gas. And for Uranus and Neptune, they are called ice giants because they are dominated by ice and cores. And we have a question that are there any planets outside our solar system? And the answer is actually yes. And these planets are called exoplanets or extrasolar planets, which are the planets orbiting the stars other than the sun. And this is a plot of the cumulative detections of exoplanets per year. And you can see that there are indeed a lot of exoplanets found so far. Actually, there have been more than 4,000 exoplanets found by date. And the first exoplanets found was 51 Pegasus b, and actually this was selected for the Nobel Prize in Physics last year. So, and how can we discover these exoplanets? There are multiple ways, but I'd like to first describe the most common method, which is the radial velocity method. Which is the key point is to use the Doppler effect. As some of you might have heard, Doppler effect is noticed when you're at home and when you hear the sound caused by ambulance. when the ambulance is coming to you, the sound is heard right with a high frequency. On the other hand, once the ambulance passes in front of you, the sound is heard with a low frequency. And this is called the Doppler effect. And we can use this Doppler method to detect exoplanets. Star and planet orbit around their common center of mass. And because the star is moving around this center of the mass, when the star is coming to you, you can see the stellar light with high frequency. On the other hand, when the star is going back to you, the stellar light is observed with low frequency. So we can detect stellar motion caused by unseen planet. And we can measure the mass of the unseen planet from the degree of the stellar motion, because the heavier planets would move the star more. So heavier planets are easier to be found. And actually the 51 Pegasus B, which was the first exoplanet discovered, was found by this Doppler method. This is a figure from my own course 1995, which are the nominees of the and this shows their observation results. The horizontal axis shows the orbital phase of the planet, and the vertical axis shows the change of the radial velocity of 51 peg-b. You can see that black dots are the measurements caused by obtained by the observation. When the star is moving away from Earth, the velocity is the positive. On the other hand, when the star is moving toward us, the velocity is the negative. And you can see that they detected the stellar motion caused by unseen planet, and in this way they discovered the unseen planet. And are there any detection methods? And the answer is yes. And the another most common way to find exoplanets is a transit method. When a planet passes in front of its host star as seen from the Earth, stellar brightness slightly decreases. And this is called transit depth. This is because the part of the planet hides the southern part of the stellar disk. So you detect the dip in the stellar brightness. And because this amount of the degrees in stellar brightness is related to the planetary size, because the larger planets hide the more part of the stellar disk. You can measure the planetary size from this transit method. So with this method, we can find a planet from the dip in stellar brightness caused by the planetary transit. And we can measure the radius of the unseen planet from the transit depths. And as I have mentioned, larger planets are easier to be found. So as we have seen, from the Doppler method, we can obtain the mass of the planet. And from the transit method, we can obtain the radius of the planet. In this case, with mass and radius, we can obtain the density of the planet. And why the density is important? This is because the density would give us a clue to the planets about what kind of planets they are. For example, if we see our solar system planets, these are the values of the density of each planet. As you might have noticed, there are many differences between the density of these planets. You can see that for the rocky planets, they have a relatively high density, like 5 grams per cc. But on the other hand, Jupiter, Saturn, and Uranus and Neptune have a lower density. So the density would give us information about their planets. And what is the next step? And I'd like to say that the atmospheric composition is the next step, aside from the planetary mass and radius. This is because there are diversity of the atmospheric composition even in solar system planets. So this is the atmospheric composition of our solar system planets, like the terrestrial planets in the left-hand side and the gas and ice giants in the middle part. And you can see that for the terrestrial planets, their atmospheres are dominated by heavy molecules like oxygen or CO2 or nitrogen or CO2. And you can see that except for Mercury, hydrogen amount is really small. But on the other hand, for the gas and ice giants, you can see that their atmospheres are almost dominated by hydrogen. And the next dominant one is helium. So there are really the difference of the atmospheric composition between these planets. And this atmospheric composition gives us a clue to infer their atmospheric evolution or composition. So the next question is, how can we measure the atmospheric composition of those exoplanets? The key is the wavelengths. So as you see during the daylight, the sun looks white, but actually the sun is emitting light of various wavelengths. So this can be noticed by when you see the rainbow or the sunrise or sunset. The sun emits a light including the various wavelengths from the blue light to the green light to the red light, but which also includes the invisible lights as well. And another stars also involved emits the different wavelengths light. And the key point is the absorption caused by atoms and molecules in the atmospheres. Atoms and molecules absorb light differently for each wavelength, and this is actually also different for each atoms and molecules. So this figure is from Howard Barrow 2012, and the horizontal axis shows the wavelengths in micron, and the vertical axis shows degree of absorption for each molecule. You can see that each molecules have the shape of the absorption for different wavelengths. So at one wavelength, for example, the water can absorb very significantly, but at another wavelength, water cannot absorb so much. And the wavelengths where the molecules can absorb more light is also different for each wavelength. So at wavelengths, if the molecule absorbs a wavelength with small molecular absorption, the light is not so decreased. But on the other hand, if the light at the wavelengths with larger molecular absorption, the light is really absorbed by molecules. And this can be used to measure the atmospheric composition of exoplanets. So if we perform the transit observation at multiple wavelengths, if we observe the planet, for example, perform transit observation at wavelengths where the molecular absorption is small, transit depth is small because the molecules do not absorb the light so much. On the other hand, if we perform the transit observation at wavelengths where the molecular absorption is large, transit depth becomes large because atmospheres absorb the stellar light significantly. So from the amount of absorption caused by atoms and molecules in exoplanet atmospheres, it's different depending on wavelengths. So that's why we can measure the atmospheric composition of exoplanets. And this dependence of the transit depths on wavelengths is called transmission spectrum. And because we know the dependence of absorption of molecules and atoms at each wavelength in advance, we can predict the transmission spectrum various kinds of atmospheric composition in advance. So this is a schematic picture, and the horizontal axis shows the wavelengths and vertical axis shows transit depths. And for example, if we assume that the atmosphere is dominated by water vapor, we can predict the transit depths at each wavelength, like the line in blue line. And on the other hand, if we assume that the atmospheric composition is like the atmospheric composition of our sun, which is called solar atmosphere, we can also predict the transit depth dependence. And if we perform the transit observation, we can infer the atmospheric composition. But for example, if we let's say we have the transit depths at this wavelength and we get this result. And in this case, we cannot distinguish between the two atmospheric models. But if we perform the transit observation at another wavelength, we can say that this planet might have a solar atmosphere. And if we perform the more transit observation at more wavelength range, we can say that this planet might have a solar atmosphere composition. So we can infer atmospheric composition from the multiple wavelength transit observation. And the first detection of chemical species for exoplanet atmospheres was achieved by Charbonneau et al. 2002, and which was the sodium in the atmosphere of HD 209458b. And this is a figure from Charbonneau et al. 2002. And the horizontal axis shows the wavelengths in nanometer, and the vertical axis shows the stellar brightness. And you can see that the black point is denotes the wavelengths where the sodium absorbs. And you can see that compared to the other wavelengths, that the wavelengths where the sodium absorbs, the stellar brightness is decreased. And in this way, they detected sodium in the atmosphere of HD 209458b. Sorry, I cannot. My keyboard freeze. Sorry.
So I stop your screen.
Thank you. Sorry.
No, it's okay.
Sorry.
Yes.
And in this way, the various chemical species have been detected so far. And the atoms and molecules that have been detected so far include various species like sodium and potassium and helium and iron for atoms, and water and methane and carbon monoxide, CO2 and titanium oxide for molecules. For example, this is a case where this is an observation where in which they detected the water and methane. And the horizontal axis shows the wavelengths in micron, and the vertical axis shows the degree of the absorption. And these triangle dots are the observed data, and this orange and blue line are the prediction from the modeling. You can see that at the wavelengths where the water absorption is located, I mean from the 1.6 to 2.1 micron, you can see that they detected the clear water absorption features. And on the other hand, they also detected a missing in this observation, which can be noticed by if you compare the blue line and orange line, where the blue line is a model without missing, and the orange line is a model with missing. And you can realize that for this observation, the model with missing matches much better compared to the blue line. In this way, they detected missing for this planet. But recently, there have been some observations which detected the very muted absorption features. This is a figure from Kreidberg et al. 2014, which conducted the observation of the relatively small planet called GJ1214b. And again, the black points show the observed data, and the horizontal axis shows the wavelengths in micron, and the vertical axis shows the transit depths. And you can see that compared to the, please look at the top figure first. And if you compare the observed black points, and if you compare the observed black points and the orange line and blue line, you can see that the water absorption feature is really muted. And the zoom up view is placed in the bottom part. And you can see that the observed feature is really muted compared to the prediction. And this infers the existence of aerosols in the atmospheres. And this is because if the clouds exist in the atmosphere, they can block the stellar light greatly for almost all the observed wavelengths. So, for example, if the cloud located in the upper atmosphere, even if we perform the multiple wavelength transit observation, clouds can block the stellar light for both the wavelengths. In this way, the thick clouds can block the light at all the observed wavelengths. And recently, the diversity of these observed transmission spectrum can be reported. This is again the horizontal axis shows the wavelengths in micron, and the vertical axis shows the transit depths. And you can see that this sample includes from the atmospheres over clear atmosphere. I mean, clear means there are no clouds or aerosols. And also the atmosphere covered with aerosols. You can notice this if you see the water absorption features wavelengths. For example, if you see the feature at 1.5 micron, where it's denoted by H2O in the top part, you can see that, for example, for the top planet like WASP-17b, which shows a very distinguished water absorption features. But on the other hand, for the planet with a blue color, does not show the very clear absorption features like the WASP-17b. And if we consider about the composition of aerosols in exoplanet atmospheres, there are many possibilities for the atmospheric the aerosol composition. We know that, for example, for the Earth, we know that the clouds are dominated. We have water clouds, but clouds existing in the exoplanets are not dominated by water because the exoplanets we can observe currently are mostly the very hot planets. So clouds are expected to exist in such exoplanets have very different kinds of composition. And this is a figure from Gawaito 2012, in which who did the modeling of the aerosol composition for the current exoplanet data. And they found that the atmospheric aerosol composition in exoplanet atmospheres can be haze or Mg2SiO4 or Al2O3 or TiO2 or something like that. So although we don't know the answer yet, but we don't know the answer yet for the composition of aerosols in exoplanet atmospheres. And before ending this talk, I'd like to mention about the future planned space telescope. And I think the most the first one I should mention is a James Webb Space Telescope, which is a NASA telescope, and which has a diameter of 6.5 meters, which means that we will become able to observe the transmission spectrum with much higher precision compared to the current case. So, for example, because the Hubble Space Telescope, which offers the most of the highest precision observation so far, has a diameter of 2.4 meters, so which is almost the JWST has almost 3 times larger diameter for its primary mirror. Also, I'd like to mention that the observable wavelength is different from the Hubble Space Telescope. And JWST can observe up to 28.5 micron, and which means we can extend the atmospheric characterization significantly. For example, the Hubble Space Telescope can observe the wavelengths from 0.1 to 2.4 micron. And what means is this means that we can extend the atmospheric characterization. For example, there are many examples for this extended atmospheric characterization, but one example is about the aerosols. I have mentioned that the aerosols composition in exoplanet atmospheres is not clear yet, but we might be able to distinguish the aerosol composition with JWST. And this is a figure from Morey et al. 2013. And the horizontal axis shows the wavelengths in micron, and the vertical axis shows the observed radius. And you can see that in the blue purple line shows the atmospheric transmission spectrum model for the water vapor atmosphere, so without any clouds. And the red line is the model for the atmosphere with a KCl and ZNS cloud. And the orange line is the transmission spectrum model for the atmosphere with haze, soot haze. And you can see that actually these all three models can match the currently observed data well. So we cannot distinguish these three models currently. But if we observe the different wavelengths, we will be able to distinguish these three aerosol composition. So let me summarize my talk. So more than 4,000 exoplanets have been found so far. And we can measure the atmospheric composition by multiple wavelength transit observation. And as I have mentioned, various chemical species have been detected so far. And also some cloudy planets have been found. And finally, the atmospheric characterization is expected to advance greatly by planned space telescopes such as the JWST. Thank you so much.
Thank you so much, Kawashima-san. So now we start Q&A session. So if you have any questions, please write down your question in the chat section. So one comment from YouTube Live is like, planet with clouds around them all the time are hard to find. Yeah, I agree. So here's a question from Nepli. Sorry if I cannot pronounce your name. There are no other gases present at Uranus and Neptune except helium, hydrogen, and methane.
There might be a different. So this only shows the very dominant chemical species. So there should be some other chemical species like C2H2 or HCN, and I think this is only shows a very dominant species. And aside from the hydrogen, helium, and methane, like the HCN and C2H2 or other hydrocarbons have been also detected in Uranus and Neptune, but a much smaller amount compared to the hydrogen and helium and methane. And also,
Are there also like clouds or aerosols in Uranus and Neptune?
yes, there are also clouds and aerosols in the Uranus too.
Okay, so if you observe those planets with transmission spectroscopy, then the variability of the spectrum is not that big.
Yes, I think so. Yes. But for example, for the Titan, which is a moon of the Saturn, even though Titan atmosphere is covered by haze, the amount of haze is not so abundant compared to maybe the planets we are currently observing. So even though there are aerosols, we can also see the absorption feature by methane or C2H2 or C2H6 above the aerosol layer.
Thank you. So the next question is how to choose high wavelengths. How high wavelength should be chosen for study? Because if high enough wavelength is not chosen, you might not be able to tell the difference between different signals.
So I suppose this is a question why the longer wavelengths is difficult to observe, or is it correct?
Can you explain me if I unmute? Can you ask her directly?
Can you hear me?
Yeah.
Yeah, so thank you for the nice talk. I really enjoyed it. So I just wanted to ask, like you showed the difference between the methane and hydrogen signals, and the difference is only visible at higher wavelengths. Like if you look at the lower wavelengths, it's exactly the same. But that was, I think, I don't remember, like around 2. But like you sort of showed some plots, like which even go to like 5 or 6. So how high wavelength do you need? Or how do you decide how high wavelength you should choose to differentiate different signals?
So which depends on each target, and because we find the currently best matched model for each planet, and the best matched model found so far is different for each planet. But usually speaking, the aerosol's absorption decreases greatly if we observe at longer wavelengths. So of course, this also depends on the aerosol distribution inside the exoplanet atmospheres. But generally speaking, I think the longer wavelengths is better. But also we have to care about the observational precision, because the star emits a light more in the shorter wavelengths, which means the observational precision is always usually better at shorter wavelengths. So this is like the balance between the difference of the atmospheric composition models and the observational precision.
Okay, thank you.
Thank you.
Okay. So one another question is like, how can one tell that there is actually no signal, easy for water, or it is actually blocked because of the presence of aerosols?
You mean that how can we
distinguish the difference of no signal or signal covered by clouds and aerosols?
So this is a very difficult question, good question. So when we don't detect any signals, which is I think theoretically there are many possibilities. So the first possibility is which is covered by clouds and aerosols. And there are also another possibilities, like if the planets are for example, if the planets are very small and the early atmosphere has been escaped already, we don't see any variation between transit depths, because if there are no atmosphere at all in the planet, there should be no signal at all. But for the planets we can observe now is mostly the gas giants. This is because the planets, as I have explained in the transit observation, the larger planets is easier to observe because of its larger size, which means the transit depth is larger. So because the larger planets hide the larger part of the stellar disk, which means the transit depth is larger. So the planets we currently observe is almost all usually dominated by gaseous planets. So the gaseous planets, and which means that it's very difficult to strip all the atmosphere already. So we expect that their atmosphere exists. In this case, I think the aerosols are the most plausible explanation to explain the no signal, or the very muted signals.
Thank you. Are there no other questions? Okay, so we have free discussion time later. So if you have any further questions, please ask her directly. Okay. So thank you so much.
Thank you so much.
Sorry, can I stop your? Yes. And here's an announcement. So I'm also doing the exoplanet research. I'm mostly doing the observational research of exoplanet atmosphere, and we all of us are very looking forward to JWST and next generation telescopes. It's gonna be game changing. So before we move on to the discussion session, I have several announcements. So we have like sister event called Nerd Night Tokyo, and they are also doing monthly event inviting not only space people but also any kind of nerd people who are doing interesting work. And their event is on November 13 online. So if you're interested in, please check them, and their Facebook and Twitter is here. And also, we Space Cafe Tokyo team started a Japanese version of the event recently, and next Japanese event is on November 15. And so this is, we started a combination of online event and offline event. So this time, oh, sorry, Ayako-san, this is offline event, right?
Yes, it's offline this time.
Okay. So the event is offline, and you can go to Hokipa Square in Roppongi. And after that, there is a video. You can see the video recording later. And the topic is about lunar rover. And Nakajima-san, will talk about his very small sized lunar rover. It's going to be very fun. So if you are interested in, please come. And our next event, English version Space Cafe, will be maybe on early December, and we will announce it later on our Twitter or Facebook and Meetup. And next time, we are planning to do the special type of event covering the topic of Hayabusa 2, because Hayabusa 2 will come back to Earth next December. So stay tuned for our announcement. So we have the social media account, Facebook, Twitter, and Meetup. So if you want to check our recent status, please subscribe us. And here is Space Cafe Tokyo team, me, Mayuko, and Ken. Do you want to say hi, Ken?
I am Ken.
And Tilina, we are the Space Cafe Tokyo organizers. And Ayako is managing the Japanese version, and Michelle is our photographer. So we are Space Cafe Tokyo team. Okay, so from now we are doing the first time trial of free discussion time. So if you don't mind, you can turn on your mic and turn on the camera also, and let's talk about anything related to space. And if you join us from YouTube, there are like 12 people joining from YouTube. And if you want to join us, please come to this Zoom meeting by this address. So thank you so much. And I'll stop YouTube live now.